Okay, so in the last video we did question A here, where we had this rectangle with one side on the x-axis and one side on the y-axis, and the vertex across from the origin was on this line y is equal to 10 minus 2x. And we maximized the area of that rectangle, and I think we found it was supposed to be 25 over 2 was the maximum area you could get. And so part B here, which we're going to do now, is saying, all right, what if we do something else? What if we put, instead of the vertex, the vertex opposite the origin on that line 10 minus 2x, this line here, what if we put one of the sides on this, and then we put the two vertices touching the x and y axes, the positive x and y axes. And they say, can we do better than 25 over 2 by making the rectangle this way? And so this is the picture here of what it's going to look like. And so the question is that if we do this instead, we set the rectangle up like this, can we beat 25 over 2? And so basically find the maximum and see is it bigger than this. And so this is rather more complicated. That just makes it more interesting, though, of course, as is always the case in math. We have this line y is equal to negative 2x plus 10 here, and we have this rectangle set up. And so we're gonna see if we can figure out what the maximum area is for this thing. So how can we pick which way to put this thing in that maximizes the area? And in order to do that, we know how to optimize functions, but the tricky part with this is going to be actually coming up with a function that gives us the area of this thing. And so the way we need to be thinking about this, we need to take, because we haven't seen this kind of problem before, we need to take sort of a structured process-based approach to this. We need to think, all right, so I want to get a function of some variable, say we'll call it x, and what is x going to be? And then how can I use x to find if I sort of, the x kind of corresponds to where I place this rectangle, because there's a bunch of different rectangles, right? As you can see, we could move this thing around. We could shift this thing. I could put, instead of this, I could have like say this, and then I would connect here. That I could have this rectangle as well, right? Which is the one that is going to maximize the area, and so I need to come up with a function that gives me the area based on kind of where I placed it. And the way that there's I'm sure tons of ways to solve this. There definitely are several ways to solve this. The way that I like to do it, or the way that I did it, was I said, okay, I'm gonna make x the point on the x-axis that I get if let me make this a nice clean line like that. Actually, for some reason it's not completing properly, so I'm just going to do it by hand, and that I think will make it straighter. X is going to be the spot that I get if I connect this the rightmost point, the point which is most in the positive x direction of the rectangle to the x-axis. So sort of how far over I went. What is the farthest point right? And as always in math, I like to get right angles and then look for things like symmetry, look for things like similar triangles, which is what we're going to use here. And so, but the idea is that I'm saying, okay, I can move this x around, right, with the triangle with the rectangle that I just drew. The x, it would have been a different x. It would have been like, the x would have been like here or something, right? As this x moves around, as this point moves around, we get different rectangles. But the key observation is going to be that the rectangle always has to be parallel. Its side, the side which has its vertices on the two axes, wherever I put it, it has to be parallel to that line, this line y is equal to negative 2x plus 10, or 10 minus 2x. That is the insight that is going to allow me to come up with a formula or a function that gives me the area of this thing in terms of x, because once I know that this thing has to be parallel, that these sides have to be parallel, and of course, because it's a rectangle, these have to be length. These have to be the same length. These are parallel. Everything is parallel. It's very nice. This lets me know that I have these similar triangles here. I have that this little triangle that I have here. This is similar to this big triangle that I have here. And this symmetry is what's going to allow me to get this function. Because whenever you have similar triangles, you get an equation. You know that the ratio of the sides of the triangles have to be equal to one another. Then you get an equation, and you can use that to isolate for variables and get functions that express quantities and stuff. It's wonderful. So also before I go any further, I see that I have this point is my x, but what about this point? Well, I don't know what this is, so before I do anything further, let me assign a variable to it. I'm just going to call this m. It does not matter at all what variable we assign to it, but the idea is that when you don't know a quantity, give it assign a variable to it, so that then you can do math with that variable. You can come up with equations that involve that variable. You can solve for that variable in terms of other variables. In this, I'm going to be wanting to solve for the m in terms of x. I could just as well solve for the x in terms of m, and then get the area as a function of m. It does not matter at all. But noticing that now that I give this variable m to this point, I assign this variable to this point. This allows me to start coming up with some more specifics about what kind of triangles I'm dealing with here. This point is going to be 2m. If that is m, this is 2m. How do I know that? Well, the slope of this line is -2. And so this is the point, incidentally, this is the point 5, 0. This is the point 0, 10. We've come down 10 and gone over by 5, as you'd expect with this line that has a slope of -2. And because of this parallelism here, because that line that connects, that is the opposite side of the rectangle, in order for it to be a rectangle, right, in order for all of these to be right angles, those sides have to be parallel. That means that this triangle in here is also, in addition to being similar to this triangle, they are all similar to this, or both of those are similar, not, I know I said all, both are similar to this triangle here, this sort of parent triangle, which I'm not going to leave shaded in purple because then it makes it harder to see everything else, but we get the idea, right? You can see that because those slopes are the same, if I go over by 5, it means I've come down by 10, right? So the amount that you went over is half the amount that you went down. Well, it means if I went over by m, right, I must have come down by 2m. So the length of this side is 2m. And then what about this little triangle here? Well, I know that it's similar to this. I know that the length of this side, the ratio of the length of this side to the length of this side here, this one here, which I'm going to erase the arrow pointing to and then redraw, that has to be the same as the ratio of the sides of that big triangle, right? The 5 and the 10, and that medium-sized triangle, the m and the 2m. And what is, I know that this side is x minus m. What about that other side here? Well, this is because this is the y-coordinate of this point on the graph. This is 10 minus 2x. So whatever x is, I get that side being 10 minus 2x, and then the base of the triangle, the height there being 10 minus 2x, and the base being x minus m. So this gives me something to work with, right? Because I know that this thing is similar. What is it similar to? I'm going to pull this triangle out and say, okay, what does this thing look like? Let me make it actually to scale. It is, if you go down, no, you're supposed to complete, there we go. If you go down 4, we go over 2. So this is m, 2m, and the Pythagorean theorem says that this is going to be the square root of 2m squared plus m squared, which is after you square everything and factor, this becomes square root of 5 times m. And this is going to be useful because that's one of the sides of the rectangle whose area we're going to want to find. But we can, it's very tempting at this point. I think a lot of people would start out by saying, okay, now that I have the similarity between this triangle here and this little guy there, I'm going to say, all right, well, 10 minus 2x over x minus m, so the height of the little triangle divided by the base of the little triangle has to be equal to m over 2m, right? Because of the similarity between those triangles. And then you can multiply through, you get a quadratic in m, you can solve it that way. But it's really unnecessarily complicated. We want to be intelligently lazy here and say, all right, instead this is just equal to 1 over 2. Right? Both of these triangles, any triangle which has it's a right angle like this and has the base which is half the height or double the height depending on which way you orient it, it's similar to this sort of canonical triangle, this sort of archetype triangle here, the 1, 2, root 2. So I can say, all right, well, let me just set it equal to 1 over 2 instead of m over 2m. I could have just canceled the m's, actually. Yeah, that's another way to look at it, is I could have canceled the m's. It is late at night, and my brain is slightly on the fritz. But either way, we end up with something which we can very easily simplify. We can cross multiply both sides by 2 times x minus m, and we get 10 minus 2x times 2 is equal to x minus m, or 20 minus 4x is equal to x minus m, or I want to solve for m. M is equal to 5x minus 20. And this is what I need. This is what I need to come up with a function of the area for the area in terms of just x, right? Because I can get the area just in terms of m, right? I know that this side, we already figured this out. This side here is root 5. M is root 5 times m. But what about this side? What about the other side of the rectangle? Well, this, Pythagorean theorem tells me, is the square root of x minus m squared, which is the base squared, plus the height squared. The height is 10 minus 2x squared. So the area of this thing is going to be root 5m times square root of x minus m squared plus 10 minus 2x squared. That's what the area of the rectangle is going to be. And that's no good if my function, so that's this area, and that's not really very useful if I don't know how to relate x and m, because now it's a two variable function. But if I can get it in terms of just the one variable x, then I'm in good shape. And this relationship here, this m is equal to 5x minus 20, is what allows me to do that. So that's very nice. Just a note, if you're wondering sort of what's going on with this, right? Like why can this? Because if you look at this, it's apparent that x in order for m to be positive, x has to be bigger than 4, and that might seem weird, right? That it might seem like if you move the x too far to the left, then the m becomes negative, and you might think maybe I have the wrong formula. If this seems weird, I encourage everyone to go on Desmos and see which kind of rectangles you can put in. Draw different parallel lines like this, right? Graph the line y is equal to 10 minus 2x. Put in different parallel lines, see which rectangles they make, and see if you can actually get the x to be less than 4. See what happens if you make it equal to 4, right? Why is this actually okay? Because you're right if you're looking at this with a little bit of suspicion, right? It's good to be suspicious of this. I'll always be doing sort of sanity checks, reasonability checks, as the quantity that I have makes sense in the situation that I'm trying to model. But in this case, it actually does, and so that's a very good sort of side project. See if you can come up with a justification. Why is this not going to be a problem? The fact that m will be negative if x is less than 4. But okay, so now let's bring this thing down here, so we have some space to do our computations, keeping in mind that m is 5x minus 20, and then we can now, this is our area function. This is a function of x and m. If we can get it just as a function of x, then we can optimize it. We know how to do that. So now let's substitute in this m is equal to 5x minus 20. We get root 4 for m in this equation. We get root 5 times 5x minus 20 times the square root of x minus 5x minus 20 squared plus 10 minus 2x squared. And I'm just going to focus actually on this bit for a couple lines and then bring the rest of it back in, because this is the part that needs to be simplified. This thing is equal to, after I expand it out, this is equal to the square root of x, or negative, what is this? Negative 4x, 20 minus 4x, after I distribute that negative sign, squared, I think, plus 10 minus 2x squared. This, I could factor out a 4 from the 20 and from the 4x, but actually I just want to factor out a 2. And the reason is so I can be a little bit sneaky and say that this is 2 times 10 minus 2x squared plus 10 minus 2x squared. Because I'm thinking ahead to trying to get 10 minus 2x squared as a factor, so that then I can take the square root and square it and get, it would be absolute value of 10 minus 2x, but because from the situation that we're modeling, x has to be in between 0 and 5, that actually isn't, we actually don't have to worry about that. We'll see what I mean in just a second. So now I square this term here, get rid of the 2, factor out the 2, right? And this becomes 4 times 10 minus 2 minus 2. Can I write a 2x properly? Evidently not. I'm looking... Sorry, I'm screwing this up because as I'm looking up here, I'm realizing I didn't write the x in. So there we go. And then this, and then 10 minus 2x. Okay, that's great. And now I can factor out the 4 and make this roots the square root of 5 times 10 minus 2x squared, because I have 4 of them plus another one of them, which becomes square root of 5 times 10 minus 2x not squared, because the square cancels with the square root. And again, this would be so the square root of the square of something would be absolute value of 10 minus 2x, but I don't have to put that in here because the x is in between 0 and 5, so it will always be a positive quantity. So I don't have to worry about that and taking cases and doing annoying stuff like this. That's a thing which is nice to note. And then let me bring down the rest of this, which we forgot about for a second while we're simplifying. So we get the area as a function of x is equal to this times this stuff, which now I can simplify and expand and take the derivative of. So first I multiplied these root 5s together, we get a 5, and then I'm going to factor out from the 5x minus 20, I'll factor out a 5 and make this x minus 4, and then from the 10 minus 2x, I'll factor out a 2 and make this 5 minus x. And this, of course, is going to be 5 times 2, which is 50. 50 times x minus 4, 5 minus x. And now we actually, this is the area as a function of x. x being, of course, the x coordinate of the farthest, the rightmost point of this rectangle on the line y is equal to 10x or 10 minus 2x here. And so we don't actually have to use calculus here. It's not necessary to resort to anything like derivatives, because this happens to be a downward facing quadratic, right? This part of it is negative x minus 5 times x minus 4. So this is a quadratic which faces downward and has roots at 5 and actually, let me put the 5 a bit to the right. Let me make this 4. It has roots at 4 and 5. And so its maximum is going to be 4 over 5 or 9 over 2 directly between the roots. So we actually don't need to take the derivative. If you want to take the derivative, you will find, of course, the same thing, that it has one root. And we have to ignore the 50, right? Because, well, not draw over it, ignore it. We have to ignore the 50 because a constant like this, a positive constant, right, is not going to change. Any constant except for 0 is not going to change where the critical points are. So I can just focus on this, and that's why I factored everything out, make things a little bit simpler. So yeah, we get just in case you absolutely have to see it done with calculus, right? We can take the derivative of this that quadratic, forgetting about the 50. This is negative x squared plus 9x minus 20. This is area of x over 50. So the derivative is going to be negative 2x plus 9, which of course has 1, 0, which is at 9 over 2, if and only if x is 9 over 2. And this negative 2x plus 9, of course, is the negatively sloped function, the negatively sloped line, which goes through 9 over 2, 0, and 0, 9. And so you can see that it goes from positive to negative at the only root, which is 9 over 2, which means that this point is a max. But you can also see that because the area function was a downward-facing quadratic, its max occurs at the vertex, which is going to be at 9 over 2, and a of 9 over 2, which is the last bit that we need to do, is actually find what is this area, because what was the goal of this? What was all this about? We're trying to do better than 25 over 2. Can we put this rectangle against this line y is equal to 10 minus 2x, and then get a larger area than if we had it with one side on the y-axis and one side on the x-axis? And so let's take a look. This is the sort of crescendo here. We have a drum roll. Can we make this thing bigger? A of 9 over 2 is equal to 50 times 9 over 2 minus 4 times 5 minus 9 over 2, which is, well, 9 over 2 minus 4 is 9 over 2 minus 8 over 2, so it's 1 over 2. So this is 50 times 1 over 2. 5 minus 9 over 2 is 10 over 2 minus 9 over 2, which is also 1 over 2. And so, wouldn't you know it, we actually get 25 over 2. Again, we get the 50 canceling with one of these 1 over 2s and making a 25. So we get actually the exact same thing. We cannot do any better. We cannot make this area any larger by reorienting this rectangle, putting it against the line, the sides against the line instead of against the axes. So hopefully you're not too disappointed by that, and hopefully the process was clear. And yeah, but the most important thing, the thing that I really want everyone to take away from this is the thought process, right? How can you think your way through these things? How you can look for symmetry, look for similar triangles, draw triangles in places, put right angles wherever you can, assign variables to unknown quantities, try to exploit symmetry, although I'm not sure how much we actually did that in this. I'm just kind of exhausted and listing Polya principles now, but Yeah, just the process is the big takeaway from this. If you see a problem like this that you've never seen before, how do you think your way through it, right? Working backwards from what you need, right? The area, what are the missing sides, right? What are the missing quantities? What do you need to find, right? This thing, this thing. Can you see any geometric things you can exploit, like the similar triangles? That's the really, really important thing about this. So hopefully this was enlightening and not too confusing. It's gone a bit longer than I planned, but hopefully the process was clear.